You can see a bunch of Symmetry applications at this website, symmetry@otterbein.edu, and I'm going to go through some of the screens that he shows in his tutorial. In the tutorial, we're going to run through different symmetry elements and show the symmetry operation associated with each element. You can see here the symbols. We have sigma, identity operation, a rotation axis, and an improper rotation axis. Along here we have the different operations. So we'll click the identity operation, and this is the simplest of all. Okay, you don't actually do anything. It might seem a bit silly, but some molecules, like this one here, don't have any other symmetry elements. There's no reflection plane, there's no rotation axis. They're very low symmetry objects. And if we didn't have the identity operation, well, then we wouldn't be able to place them in a category apart from to distinguish them from other molecules. So here we have CHFClBr. So let's assume that carbon's in the center. We've got a hydrogen, that small white one. A chlorine, I guess that would be the green one. Fluorine, no, this would be bromine. Bromine's a red liquid, and that's fluorine over there. If we look at this one, it's a different shape, but again, it only has the identity operation. You can see it looks a bit like a carbonyl, except that this molecule is not planar. Okay, we'll just bring it back to the center again and bring it up there. So we got what looks like a sulfur double bonded to an oxygen, and then we've got a chlorine and a bromine. And as before, there's no mirror plane. If both of these atoms were bromine, or they were both chlorine, then we would have a mirror plane down there, but we don't. And because it's not a planar molecule, in fact there's no mirror plane down the middle either. The proper rotation, the CN axis. Here's what looks like a water molecule. If I rotate it 180 degrees, you can see that we end up with a molecule that looks exactly the same as when we started. So there is a rotation axis. Now I just rotated this molecule by 180 degrees. If we divide 360 by 180, then we get 2. So it's a C2 axis. You can perhaps imagine that if I took an ammonia molecule, NH3, and I rotated that by 120 degrees, then that would demonstrate we had a C3 axis, because again 360 degrees divided by 120 is 3. So let's have a look at the axis. There it is, going up through the middle of the molecule, and I can rotate about that axis. There we are. Okay, we can look at it from a different angle. Let's look sideways on. Oh. There, we'll look sideways on and rotate it, and there you can see it. And let's just look from the top. Okay, so we're looking down on the oxygen here, and we'll rotate it again, and you can see we're turning about that C2 axis. We can look at ethane as well. Now ethane is CH3CH3, or if we turn it we can see what's what. And we're in the staggered conformation here. You can see that this hydrogen atom comes up between these two hydrogen atoms, but I'll get a good angle. There's quite a good one. So perhaps you can see now ethane has a C3 axis here, and we can rotate about the C3 axis there. Okay, it also has a number of C2 axes. Okay, so C3 is the highest axis, so that would be our molecular axis. So we would normally orientate this molecule to have the primary axis aligned with the Z axis. Get there. So I'm trying to get an angle where we still have some perception of the depth. That's about as good as I'm going to get it, I think. Yeah, okay. So I'll rotate once again, and you can see, there we go. Now we have a C2 axis. There are 3 C2 axes. There's one coming through the middle of the molecule like that, and if I rotate about that one, you see that, so that's a top to bottom change there. There's another C2 axis through the same point but aligned along this axis, so we're hitting that carbon and hydrogen and that carbon hydrogen bond down the middle. We can rotate about that one, there we go, and we can look at the third one again. Okay, again each of the arms on that C3 axis give us our proper rotation. So in a proper rotation, C3 proper rotation, we have a C3 axis and then 3 C2 axes as well. Now we'll have a look at reflection. Fairly straightforward one to see. Now this is our ammonia molecule. We'll bring it up so we can see that it's ammonia. If you recall our discussion, this has actually got a C3 axis up the middle there. But here, this time, we're looking at the reflection operation. So if this is the C3 axis, then the molecule is correctly orientated upwards this way. Imagine you have a lone pair on the top there. We have a vertical reflection plane in the plane of the screen here. There it is, and I'll just turn this so you can see, get perhaps a better idea for what it looks like. There we are. Okay, so it's coming down between that nitrogen hydrogen bond, one sticking out the front and this one is sticking out the back. I can reflect through that, and I'm just going to turn slightly to about there. If I reflect through that plane there, let's see if I can do that again from here. I'll reflect through that plane. There we go, you see, and this one at the front, this one at the back, they swap positions, but in the end result is that the molecule looks exactly the same as when we started. There's a second plane, another vertical plane. This time, you see, our first one was coming through that nitrogen hydrogen bond. The next one is coming through the next hydrogen nitrogen bond, and we can reflect through that there, and we have a third one, of course, through this hydrogen nitrogen bond. And you see we've got a plane going through each of these NH bonds. Reflect through that. Okay, looks a bit like a beach ball, doesn't it? Have a look from underneath and you can see perhaps that those planes all bisect the C3 axis. Now we'll have a look at the inversion operation. You came across this before when we were applying the inversion operation to determine if two orbitals had U or G symmetry, if you recall. Now we're going to apply the inversion operation here. Now this goes for a single point called the inversion center. This particular molecule does have an atom right in the inversion center, although that's not necessary, and I'll show you an example in a minute. So this is the inversion center right in the middle on that C4 axis. The inversion center has the symbol I. When we take any point on this molecule, we're going to take a point on this atom here. If we go into the inversion center and then come out on the other side an equal distance, when we do that, there, you see, we end up with exactly the same molecule as we started before. There's the inversion center, and now I'll take each point on the molecule, carry them through the inversion center and out an equal distance on the other side, and we end up with the same looking molecule. Now, as I said, this molecule has an atom at the inversion center, but that's not necessary. If we have a look at ethane, now this is our staggered conformation again. Okay, can you see the inversion center here? Now this time the inversion center is going to be in the middle, and it forms where the bond is. Let's see if we can see where it is. No, it's not showing. Okay, let's invert. Okay, there's the center, and there's the inversion, you see. So each point, this would come into here, out an equal distance on the opposite side. So let's see if I can come to there. Okay, so this will go down into that and come out the other side. We'll invert again. You can perhaps there. Okay. Now we saw the example with tetrachloroplatinate. This was platinum with 4 chloride ions on it. Be TdCl4 2. Oh goodness me, 2 something or other. We have the atom in the inversion center. In ethane, we have the inversion center falls on a bond, but even that's not necessary, because we'll have a look at benzene. Now, benzene's a ring structure. Okay, there it is. And we'll have a look at the side, you see. I don't particularly like the representation of this double bond system, but nonetheless. Without looking at an animation, you can probably see that if I take a point from one of these hydrogen atoms, go into the inversion center at the center, out to the other side, I'm going to swap or exchange these 2 hydrogen atoms, and that's going to happen for every point on the molecule. The other CH bonds are going to swap places with these ones, and there is the inversion center right in the middle. If we invert through there we are, and we end up with the same molecule we started with. So benzene has an inversion center. When we invert, we perform an inversion operation. The last symmetry operation we'll look at is the improper rotation. Now, this is a double operation. We first of all perform a rotation, and then there's a rotation, and then there's a reflection. We don't go all the way around. So for the improper rotation, this is the final one. It's only more complicated because it's not a single operation. We do 2 operations, one after the other. The first operation is a rotation through 360 divided by n degrees. So this molecule here, ethane, in the staggered conformation, has an S6. So n is 6. If I rotate the entire thing by 360 divided by 6 through 60 degrees, this hydrogen is going to end up here right in the middle, this is going to end up here, so nothing's going to line up. So the rotation operation itself does not give us back our starting point. However, if you can imagine this is now here, and then we reflect through the plane perpendicular to the rotation axis. So here's the rotation axis. I think we can show it. There's the rotation axis, that thin line going there. So we rotate about that, and then this plane here, well, that's our reflection plane, and it's perpendicular to the rotation axis. So we rotate 360 divided by 6 degrees, and then we reflect through this plane, and that will bring this CH bond exchange with this CH bond, and this CH bond will go around to the next one. Let's watch that happen. Now we'll rotate and then reflect. We'll see it again. Rotate 60 degrees and then reflect through the plane. Rotate 60 degrees and then reflect through the plane. Let's look at it from another angle. Okay, I think that would be a good one. And we go again, rotate by 60 degrees and then reflect through that plane, and we end up with the apparently unchanged molecule. Rotation, reflection. Rotation, reflection. You can do the same thing to, well, quite a few molecules have this. An octahedron does, and methane, which of course is a tetrahedron. Now, methane has a C4 axis. Okay, there's a C3 if you look down that bond. Okay, but we have an S4 improper rotation. I'll show there. Okay, so there's our rotation axis, and then this is the plane perpendicular to that. So if we rotate this and then we'll reflect that through the plane, we can watch that rotation, reflection. Did you see what happened there? We'll look at this one here. Okay, first of all, rotate is now in the front, and then it comes to here. So this rotates, comes to the middle, and then reflects, and it falls into this position. Rotation and reflection, and we end up with the same molecule. Now, the tetrahedron actually has 3 of these axes. There's the first one. The second axis is here. Okay, so these two here, they're going to rotate by 360 degrees divided by 4. They're going to rotate 90 degrees, and then they're going to reflect through the horizontal plane. There it goes. Rotation, reflection, rotation, reflection. And the first one, rotation, reflection. Now, there's one more S4 axis here. And we're looking straight down the axis. It's the one that's coming out of the molecule towards us. I'll just turn that. Okay, and this is getting a bit unclear, so I'm going to remove the first two. And now we've got this axis. If I rotate, rotate and reflect, got the first one back and the second one back, and now we've got all 3 axes, all 3 S4 axes, and there perhaps you can see the tetrahedral shape of this molecule, and we can rotate and reflect. Okay, there.